Well, thanks a lot for the invitation. It's great to present at this conference. This joint work with Jeroen, who is also in the audience, and he will address questions on the chat board. So let me motivate what we do in this paper. It's clear that screening is a central topic that has been widely researched in economic theory and also shows up in lots of empirical work. And there are many beautiful seminal papers that started the literature. You can think about in the monopoly case in Musan Rosen and Maskin and Riley, also competitive versions in Rothschild Stiglitz, etc., etc. Huge literature that follows. Now, something that has not been as well researched as those benchmarks is the case in which there is screening, there is competition, but among a small number of oligopolistic firms that are heterogeneous in technology. I will specify that. And this is what this paper is about. So we are going to present a model that will be sort of a natural extension of one of the monopoly and the incomplete information problems, but to an oligopolistic setting among heterogeneous firms. And there one can ask several questions. For instance, what are the properties that any equilibrium must exhibit? Do pure strategy equilibria exist in this model? What are the effects of entry, mergers, etc.? So, and we are going to provide answers to all of these questions and more actually. So here are, just to give you an overview, what the main results of the paper are. We have three parts in the paper. In one part we say, okay, what are the properties that any equilibrium must exhibit? These are the necessary conditions for equilibrium that we have here. Then we, as you will see, among those necessary conditions, there will be some local ones, and we are going to try to think about the case in which, well, suppose that a subset of these local conditions are satisfied by a strategy profile. Is that a strategy profile an equilibrium? And we are going to provide the result on that. And then we are going to show that an equilibrium in pure strategies exists in this model. And in the third part, that we call implications and applications, we are going to address issues such as welfare when we compare our setting with incomplete information with the benchmark case with complete information. We are going to also look at the effects of entry into the model, into the market, and whether in the limit we get the sort of competitive limit. And we are going to also look at the effects of mergers. I will try to give you at least one of these three applications, if you want, today in the talk. I don't have time to go over the literature review. There are some notable precedents to what we do. The one that I'm going to come back to or probably mention later is Julien, who does the principal agent problem, where the agent has a type-dependent reservation utility. That's a single principal problem. In our case, this type-dependent reservation utility will arise endogenously as part of the equilibrium in the oligopoly. So, let me go directly to the model here. The model, as I told you, is a natural oligopolistic version of this monopoly and the incomplete information papers like Musan Rosen or Maskin and Riley. We are going to have a large number of agents. They could be customers or workers. Our formulation accommodates both, and we have examples in the paper. Each agent will have a type on 0, 1, distributed according to a CDF H and density H, little h. And H and 1 minus H will have some standard law concavity assumptions. Each agent will choose an observable action A that is positive, that is bigger than or equal to 0. So there will be no moral hazard in the model. And the utility for the agent, if he chooses action A and his type is theta and receives a transfer T, the transfer can be positive or negative, will be given by this function here, quasi-linear. And the only additional assumption we make here is that A and theta enters in this multiplicatively separable form. Regarding firms, there will be these n principals or firms, and the payoff will consist on these two parts, well, transfer, and also this function v n of A that you can think transform the action that an agent chooses into, if you want, a revenue, or it could be a cost for the firm depending on the application at hand. And we are going to assume, and this is crucial for our purposes, that this function script Vn will be strictly supermodular in A and N. And to avoid further issues of complementarities, we are going to assume that profits are additively separable across all the types that are served by any given firm. This is just notation because, as you will see, I will forget about this script V functions. The match surplus between a firm N and an agent with type theta who chooses action A will be given by this V N of A plus this A times theta, where V N of A is just the sum of these two script functions here. And we are going to impose as an assumption that this Vn is strictly concave, and moreover satisfy some boundary conditions that are not just technical, just to ensure interiority of solutions. So these are in terms of principles and the agents in the model. What else do we have here? Well, each firm will offer a menu, a pair of functions. This alpha function is a function that for each theta, it instructs what will be the action that the agent of type theta will choose, and similarly for the T is the transfer. We are going to assume that contracts are exclusive, so each type of agent can deal only with one firm, and they cannot depend on offers of other firms. We know that this is not without loss of generality, but we think that competitions on via using menus is economically realistic and worth exploring further. So, but we are aware that we are imposing a restriction here. So instead of thinking about a menu as this pair of function alpha and the transfer, the standard thing that we do sometimes is to think about it in terms of the allocation, the alpha function, and the surplus that that firm N gives to each of the times. So this is what we are going to do henceforth. We are going to forget about the transfer for now. As incentive compatibility for a menu is, as usual, the alpha N will be increasing, and Vn will satisfy the integral constraint given by this functional form here. One piece of notation, capital Sn will be the set of all incentive compatible menus for firm N, and little sn will be strategy for firm N if you want, which is a menu. And capital S is simply the set of all strategy profiles in the model. Now, what is the profit that firm N derives if it deals with type theta and it gives to that type a surplus given by a number V0? Well, it will be given by this function pi n that I will use throughout, that is simply given by match surplus between the two minus the utility you give to that agent. Henceforth, also as to economize notation, I will write pi n as with arguments alpha and v instead of alpha, theta, and v at theta. Something more important for our purposes is that we wanted to make sure from the outset that every firm was going to be active in equilibrium. So we assume something we call relevance, and that is that each firm is uniquely best at serving at least some type. So what we assume is that for each n, there is a theta such that the maximum match surplus that this firm could ever provide to type theta, we call this v star n of theta, is strictly bigger than the maximum that other firms can provide. And so essentially each firm, at least in terms of efficiency, is uniquely best at serving an interval of types. And this can be mapped also into an interval of actions, given the strict supermodularity of Vn, at which firm N is the most efficient for any action in this set, in this interval. So relevance, from now on, something we assume, it buys us that all firms will be active in equilibrium. Now, the game is fairly simple. Firms will simultaneously post menus, Sn of alpha and Vn, and agents will observe the menu and will sort to the firm that offers the contract that each of them likes the most and announce their types. And we are gonna say that firm N wins the type theta if it offers to that type a surplus that is strictly bigger to what the rest of the firms offer. This V naught N is the maximum of other firms here at type theta, and loses that type if you have the strict inequality in reverse way. And we assume that ties are broken equiprobably here. So the final slide of the model is that we are going to denote capital script pi, the expected profit of firm N, when the strategy profile is S. This is the profile of the menu profile given by S. And since we assume that profits are additively separable across types, it will be the profit per type, weighted by the density of that type, yeah? And also weighted by the probability that firm N wins type theta given the strategy profile S. And then you integrate over that. And since we already subsumed the behavior of every type as being incentive compatible here in the description of the set of menus that we allow, then we can think of this as a game just among the firms where a strategy profile is a Nash equilibrium is if each menu offered by the menu offered by each firm N satisfies the best response property, given what the others one are choosing. Two comments here. The first one is as you can see from what I have described, we are restricting attention to pure strategies. Nevertheless, we do have also a result on existence in mixed strategies, but in all the talk, I'm going to just focus on these. And we're also going to impose a refinement. We don't, so we're going to focus on equilibrium that passes this refinement. We don't want to deal with offers that a firm makes that loses money if accepted, but is accepted by a zero measure set, but nevertheless imposes participation constraint on the other firms. So in order to avoid that, we are going to focus on equilibrium that passes the refinement that we call no extraneous offers, NEO, and that essentially says that alpha is continuous with actions in the set of actions that at which N is the most efficient. And I will basically use this essentially in the necessary conditions. That will be the main use. So that is the game. If there are no questions at the model, if there are no questions about the model, so the only thing that I know that there was some notation there to keep track of, but the only thing you have to remember is that this is sort of a natural oligopolistic version of the standard monopoly problem under incomplete information, with this oligopoly that among heterogeneous firms. So let me go to the necessary conditions, that is, properties that any equilibrium that satisfies this refinement must satisfy. The first two are quite natural, and actually the first one doesn't depend on being in equilibrium. Basically what we have here is that there will be positive profits for each firm, in the sense that the probability that a firm will serve a type on whom that firm strictly loses money is zero. And the intuition is pretty simple. If you give me any incentive compatible menu, pick the contracts on which that are giving you strict losses, get rid of them, and whatever remains still will satisfy the constraints of the problem and will essentially give you positive profits in the weak sense. And this relies on something that was implicit in the description of the model, namely that the model exhibits private values. That is, firms do not care directly about the type of the agent, they care indirectly through the agent choices. And since we assume relevance as well, that is that at least each firm is strictly best at serving at least one type of agent, then actually every firm in equilibrium will make a strictly positive expected profits, and there will be no cross-subsidization. That's one property. And as I said, it's a property that goes beyond just an equilibrium property. The second property, which we call no poaching, is also very natural. It says that in equilibrium, it shouldn't be profitable for a firm that is not currently winning a type theta to mimic the offer that whoever is winning that type is making and essentially poach that type from that firm, if adding an epsilon. So basically, no poaching is a property that ensures that there is, in equilibrium, there is no incentives to capture inframarginal types. So it's a very natural property that must obtain in this setting. And it also, it formally tells you that if you think about VO as the surplus that is being offered in equilibrium by all by the firms here, let's think of this, the upper envelope of all the surplus, at type theta must be bigger than or equal to than the match surplus that the second largest firm with the largest V could offer at the equilibrium action that is being offered to this type. And this imposes also an upper bound on the profit per type that a firm can obtain. Basically, it's bounded above by the efficiency that this firm has compared in terms of the V compared to the other firms in the market. Okay, this one is more interesting, although it's also intuitive. So any equilibrium in this model will exhibit what we call positive sorting. That is, firms with a higher index N will serve higher intervals of types. There could be overlap, but this overlap is only between two adjacent firms. And when there is an overlap, then competition, the logic of Bertrand there kicks in. The two firms offer a pooling contract on the overlap interval, and they make zero profits. But there is a non-trivial interval on which a firm is uniquely serving those types in the model. And if firms are sufficiently differentiating, then there will be no overlap. That is, these intervals here of overlap here, where there are ties, will collapse to a singleton. And basically, we get a strict positive sorting in the market. That is that firms serve, higher firms serve strictly higher intervals in that case. And even without NEO, this property gives us continuity of the function alpha, the allocation that tells you for each type what will be the action that you're going to give whenever firm N beats the other firm. So it's a property of best response, this continuity here. It doesn't require the equilibrium, or it doesn't require the NEO property. Okay, just to give you a graphical depiction of how an equilibrium might look like, think about the case with four firms. And suppose that the four firms are posting the following a schedule of surplus. V1 for firm 1, this V2, the firm 2, firm 3, these ones should go up to here, and similarly for firm 4. Yeah, so essentially a function V that determines that tells you what is the surplus that each type will obtain. So in this particular case, there is a strict positive sorting, in the sense that notice that there is only one boundary point here at which they strictly cross any two of these schedules. And if there were ties, there would be some tangency here over an interval. And notice that, for instance, up to this point, the firm offering the highest surplus from 1, so from 1 serves this interval. Notice that firm 2 beats everybody else on this interval, so it will offer or serve this interval of types. Firm 3 offers this, beats on this interval, so it will essentially serve this interval of types. And firm 4 beats on the rest of the type space here. So that will be one example that, or how an equilibrium might look like without ties. So we have the three properties that I just told you. One is a positive profits that is fairly general. No poaching, that it talks about trying to capture inframarginal types. Positive sorting, that tells you sort of a global structure of how the equilibria look like. And the last two properties that I'm going to emphasize basically are local properties that must hold and that pin down the actions that each firm offers in a menu over the segment where they beat the other firms, and moreover, how the local conditions that pin down the boundary points. So this one, it's a bit of a mouthful, it's a definition here, but as you will see, this is something that is extremely familiar to all of us with a minor modification. So notice that we have here a few firms and they are screening. Yeah? So at some point, the efficiency versus information rents trade-off must show up here, and it shows up in this condition that we call internal optimality. Let me go over the definition. So we are going to define gamma as the solution to this equation. That is the action that this equation clears for type theta, given this parameter that comes out of the blue here, kappa. This kappa is between 0 and 1. we are going to say that, and before I define internal optimality, if you put a kappa equal to 1 here, and you pass this H to the other side, this is standard monopoly condition, yeah, of efficiency versus information rents. So the difference here is that this kappa can be something between 0 and 1, or can be 0 in this case as well. So what is internal optimality? We are going to say that an equilibrium satisfies internal optimality if for each firm n, there is one of these scalars kappa n in this interval here, that is where the lower point is at the CDF evaluated at each lower point here, and such that kappa 1 is 0, capital N is 1, and such that the menu that is being offered in equilibrium by firm n coincides with gamma on this interval here. And any equilibrium will exhibit this property of internal optimality. So I will tell you a couple of implications of this. The first one is that if we think about firm n, kappa is 1. So notice that that means that this side here is positive. That means that pi sub A is positive for every type that we plug here. So firm 1 will distort downwards the action away from efficiency. At efficiency, you have pi sub A equal to 0. If you plug here kappa 1 equal 0, which is what happens for firm 1, the other extreme firm in the market, then this will be negative, and that means that pi sub A is negative, so this firm will distort the allocation or the action that it has for every type upwards. And for any intermediate firm, kappa will be intermediate here, where I'm going to show you in the next slide that it will be strictly between these two bounds here. So that means that there will be a theta naught such that firm n will distort downwards to the left of theta naught and upwards above theta naught. And although I have on the next slide intuition for that, the idea is also familiar from the literature on countervailing incentives, Julien or Maggie and Rodriguez-Clary. So one way to think about it is that interior types or middle types for a firm, for one of these intermediate firms, are the ones that are the most profitable ones. And in order to extract more rents out of that, you distort upward to one side, downward to the other side to make the offers of adjacent firms or types, the other types, less attractive to them. Now, I have to tell you one technical point about this, because the proof of this internal optimality condition relies on the solution to a relaxed problem. So you don't have to focus much on anything. I will just tell you that this is a relaxed problem for firm n in the model given that is serving theta L and theta H. It is relaxed because we don't have the monotonicity constraint on alpha. It is also relaxed because we only have the constraint here that this must be bigger than V naught n at the endpoints, but not in the middle. So it's a relaxation of the true problem that firm n faces here. And this problem has a unique solution on the interval theta L, theta H that satisfies the IO form that I told you before, the internal optimality form. And we can extend elsewhere, if you want, define it as you wish. For instance, could be extend with constant action above and below. And this is the only thing that I want you to remember, because I will come back to this. Think of this R as the value of this relaxed problem when the boundary points are theta L and theta H. That's the only thing. Remember R. So how do we prove this result? Well, we say, suppose that you have a candidate menu, a candidate equilibrium menu, a menu profile, and one of the firms do not satisfy internal optimality with the menu that is posted. Then we can perturb in a feasible way that menu in the direction of the solution to the relaxed problem and strictly improve the profits of the firm. So this is the way we show that any firm will satisfy, in any equilibrium, IO will be satisfied. And again, this is a local condition, yeah? That's the thing. From here, if you remember, I assumed that H and 1 minus H were strictly concave. This gives us this gamma is strictly increasing, so it's very nice. And it's strictly decreasing in kappa as well. The final local condition is the so-called optimal boundaries that essentially gives us sort of a local optimality condition that the boundary points of the interval served by each of the firms must satisfy. For firm 1, you discard the lowest one, this one, because theta L is 0 for the, and for the highest one, you discard this one because the highest type it served is theta equal to 1. And again, the intuition comes from a perturbation argument that I will not say now. But unlike no poaching, this optimal boundary condition that you can think as a first order condition that must be satisfied at the endpoints is about local changes of which interval is served. And it gives us as implication that the most profitable type is interior, that the kappa is strictly between these bounds. So we have this upward and downward distortion that I told you before, strictly biting. And the other byproduct is that each firm will make strictly positive profits on the interior of the interval it serves, and if there is a strict positive sorting, even at the boundary points. So firms are making money on every type that they serve. So any equilibrium satisfies positive profits, no poaching, positive sorting, internal optimality, and optimal boundaries, the last two local conditions. So what we want to do now is to say, well, suppose that I have a strategy profile. This is a very important exercise for us. Suppose that I have a strategy profile that satisfies a subset of these necessary conditions. Can I be sure that this will be a Nash equilibrium? That's the idea. And suppose that I prove that, can I be sure that a Nash equilibrium exists? These are the two questions that we address here. In order to do that, we are going to rule out ties at boundaries, because having these intervals of ties are complicate things a lot, especially because of the interval that is served may not vary continuously in the strategy. And we are going to assume that we have something that we call stacking. This can be justified from primitives very easily. In some cases, depending on how you specify the functions v, it can be just a parameter that you alter there. But we are going to assume that for every firm, the lowest gamma function that firm n plus 1 could use, remember that this happens when kappa is equal to 1 because gamma is decreasing in kappa, is strictly above the highest gamma function that firm n could use, which is what happens when kappa is equal to 0. So essentially, this can be guaranteed if firms are significantly differentiated. And that gives us a strict positive sorting here that with no ties. Now, we say that given the strategy of every other firm and given a firm n, two strategies are equivalent if they only differ where they are not winning types. So in the irrelevant parts of that strategy, if you want. So given that notion, we have the following, which we consider a central result of our paper, that under stacking, then if I have a strategy profile that satisfies positive sorting, internal optimality, and optimal boundaries, then that strategy profile is equivalent to a Nash equilibrium. That is, the strategies only differ where they don't win. And a Nash equilibrium exists, and we have existence here. So before I tell you more about this result, let me tell you a few things. First, as a byproduct, since these rely on these local conditions, basically, this result affords a very easy numeric analysis. Essentially, the equilibrium problem reduces to a set of simultaneous equations that must be satisfied. And basically, the unknowns are scalars, boundary types, the kappa, and the initial surplus that each firm gives. And all the examples that we have in the paper are computed based on this result. The sufficiency result is hard because in our original problem, the function pi of n is not quasi-concave. So we cannot be sure that local conditions, even a priori, it's not intuitive that local conditions will suffice. Local conditions such as IO and OB will suffice for a strategy profile to be an equilibrium. And existence is hard because payoffs are discontinuous, yeah? But we know that there are theorems for discontinuous payoffs. But on top of that, we have the lack of quasi-concavity here. And that at least didn't allow us to use an off-the-shelf result to prove it. But we're going to do here something that is much more elementary, if you want, but that requires a lot of work. So what we want here is to move from the choice of n of a menu, that is functions alpha n and vn, to a two-dimensional problem where we worry about choosing optimally theta, the boundary points theta n and theta h. This is what we want. By I/O, since we are assuming I/O in this result, we know that alpha n is equal to a gamma function, at least on the interval served, and then we can focus on the choice of this. How do we proceed? We first restrict menus as follows. We say, well, based on what we learned from the necessary conditions, let's impose some reasonable restrictions on the menu. We are going to assume that alpha is continuous with the actions in this bound for each theta. And also, we are not going to allow firms to post a surplus that will lose money. That's all we are saying here. The next step is, well, okay, let's assume C1 and C2. Then we are going to relate our original problem, which is, I'm not going to go over all this, but which is try to find a strategy that maximizes the expected profits in terms of finding a menu, to a problem that looks like this. Maximize this function R, which is the value of the relaxed problem I told you long ago, but now optimizing with respect to theta L and theta H. And this proposition essentially connects the two problems. Basically, a maximum of this problem plus the derived menu that you can construct by solving the relaxed problem, yeah, will essentially connect very nicely to the any maximum or any best response of solving the original problem. One issue that remains is that in order for this to work, we need this problem to have a unique optimum, a unique maximum. And this is where most of the work lies in the paper. It does have a unique maximum, but we have to work very hard. Why? Because R is not quasi-concave. In fact, it has local minima, but it has local minima where in places where R is negative. So, and we know there are positive profits in the model. But if we restrict attention to the subset of theta L, theta H, on which this is positive, and we know how to pin down that, then we show that we have enough quasi-concavity to show that there is a unique optimum, there is a unique maximum, and that maximum is captured by the local conditions. So this is essentially where all the work of sufficiency lies. So I'm not going to present existence, so let me give you a very simple outline of how we proceed, because once we do all this work, then sufficiency comes very naturally here.
Just, you have 10 minutes.
10? Okay, so let me do the following. If you buy the sufficiency and existence, let me go over the applications and implications, because I really, this new stuff that that Jeroen and I did, and we are really excited about that. But basically, just one comment. Once we know that we can reduce the problem from an infinite dimensional problem to just essentially choosing scalars here, then existence becomes much simpler. Then now we can appeal to a standard fixed point argument, and essentially this is what we do here. We use Kakutani-Van-Glitsper once we essentially have available the sufficiency result where we lower everything to a two-dimensional case.
So before you go to applications, do you have any thoughts on uniqueness of equilibrium?
No, actually, that's a very good point. And even as I told you that okay, so let me put it this way. We haven't explored uniqueness much, but the equations in unknowns that I told you here,
yes,
yeah, these are highly nonlinear equations. So it's hard to ensure, at least from working on those equations, whether we have uniqueness in that case. We can tell you that we have a unique equilibrium if we have two firms, and that we know. Mm-hmm. But beyond two firms, these equations become hard to at least manipulate analytically. Then in the examples that we compute, there is always a unique equilibrium. But basically, whether it's a general property or not, I don't know.
That's a yeah. Sometimes there's a computer proof of uniqueness.
Yeah, no, this is not a proof. So, but for two firms we do.
Yeah, I understand.
We do.
Okay.
So let me move on then. If you and skip sufficiency or the outline of the proof of sufficiency and the outline of the proof of existence. So in the minutes that I have left, I will focus on two applications. The first one is welfare effects, and the second one is mergers. And so here's the basic idea of welfare. We consider the complete information version of the model and compare how welfare, for instance, of different types are affected by complete versus incomplete information. If we only had a monopoly in our case, things would be trivial. The agents will lose all the information rents under complete information here, and the monopoly extracts everything. So that's pretty easy. But in our setting, we still have that since we have complete information, if we have complete, and in our setting, but with the complete information version, agents again will lose the information rents. But now, poaching by firms is easier because they can do it type by type without worrying about incentive compatibility. So competition is more fierce, and the outside option of each type is higher. So basically, we have these countervailing forces. And what we can do, we can pin down exactly the intervals of types that benefit or prefer complete information to incomplete information. That is, the force is strong enough here that essentially they end up better off without having private information. And we also have pinned down the segments of types that could be empty, where those types prefer incomplete information. And actually, we can produce examples where all agents will prefer strictly the complete information because of this second force. So that's one result that we have, and I had some graphical depiction of that, but I'm going to skip this because I only have 5 minutes, I think. Yes?
8 minutes. Now,
okay.
Sorry, 6 minutes.
Say again?
6 minutes.
6, okay. So in the last few minutes, let me, and I want to leave for hopefully a couple of minutes for questions if there are questions. But in the last, one application that we explored is what are the effects of mergers in our setting. So as a building block, we analyzed the case in which we have a single firm, but controlling all the technologies in this market. Basically, think about this as just a monopoly with multiple plans, which is sort of a nice extension of the Econ 101 type of problem. And we assume also, in order to make the problem non-trivial in this part, that the monopolies faces a type-dependent outside option that is first shallow and then steep in order to mimic what would be the effects of stacking. And this outside option, if this was only a subset of firms merging, would be coming from the rest of the firms in an oligopoly. So what we show is that this multi-plan monopoly can be solved exactly in the same way, barring some differences that are technical, and all our previous results apply. That is, the multi-plan monopoly will serve an interval of types, can exclude at both ends, IO will hold with a single kappa, and optimal boundaries will pin down uniquely these boundaries here. The only difference is that there will be a finite number of jumps in gamma at the points where the firm decides to use one technology versus the other one. So there are some internal optimality boundaries that one has to deal with here. Once we have this benchmark case, then here's what we do. We say, well, suppose that we have an oligopoly where each firm controls one technology, and we compare this with the solution of the multi-plan monopoly. Think of this as a merge here of all the firms. And we do two things. First, we say, well, suppose that we impose a must-serve condition on M. That is, that both in oligopoly and after the merger of all these firms, they must serve exactly the same set of types. Yeah? So something imposed by an antitrust authority. Then we show that all types in the interior of this interval are strictly worse off under the merged firm. And an interval of low types receive a strictly lower action, so there are further distortions at the lower end, and also further distortions at the upper end. And the basic idea is that now that for the merged firm, there are more interior types to extract rent from, and this leads to further distortions above and below. So the takeaway from this is that a must-serve condition imposed by an antitrust will not be enough to protect consumers after the merger, because what the merge fund does is to lower the surplus that gives to every type, and every type is strictly worse off. Then we say, well, let's get rid of this must-serve condition. Without that legal constraint, what we show, and this is the content of this theorem, that is surprisingly difficult, is that the multi-plant firm will not only lower the surplus, but also will shed some types at both ends. So will serve a strictly smaller interval of types. So this is what we obtain here. And it's essentially this shedding of types is an exercise of market power, if you want. So the final thing that we do, and this is, we have some clear ideas of the difficulties, but we have many computed examples to understand the problem. It is what happens if M, instead of being a monopoly that all the firms have merged, what happens if it is just a subset of all firms and the rest continue to be the single firms, the individual firms in the oligopoly. Then here there are countervailing forces. And let me tell you why, because we think it's quite interesting. On the one hand, the result that I just presented here, that is embedded in this theorem, that is that M, the direct effect is that it will lower surplus to everybody and reduce the interval of types that it will serve. Given that, other firms now are tempted also to lower the surplus, since they face a lower surplus competition from the merged firm, and that would lead to every firm lowering surplus and all types being worse off now. What is the countervailing force? The countervailing force is that the merged firm will distort further at both ends, so it will become less differentiated compared to the adjacent firm outside the merged firm. And this will tempt the outside firm to raise surplus a bit and bite additional types that are served by the merged firm. So you have these two countervailing forces. In all the computed examples that we have, the merger essentially reduces surplus to everybody, and the merged firm sheds types. So here is one computed example, and with this I will end. Here is the upper envelope of the surplus offering our oligopoly with 4 firms, the picture I showed you before. The next one is the case in which firm 2 and firm 3 merge. So notice that compared to this point where you transition from firm 3 to firm 4, here the transition occurs before, so the merged firm shed some types. Here, instead of the transition from firm 1 and firm 2 here, the transition from firm 1 and firm 2 occurs here, so the merged firm shed some types also at this end. And then we compare this problem, this equilibrium, with the case in which we just make firm 2 disappear from the market. And this will be the case in which we have the oligopoly with firm 3, firm 2, firm 1, and firm 4. And in this case, surplus is even lower. So basically, something that is common in the antitrust literature, the failing first firm defense, is validated by at least the computational examples we have.
Well, we have reached the end, but if you
Perfect.
have...
Perfect. So I'm basically done.
So there are no formal questions in my Q&A box, but I'm sure people can send you emails if they have questions.
That's perfect.
And with that, I want to thank you and see you tomorrow, everybody, at 9:30 in the morning